Find the x-intercepts of the graph of the function without graphing the function. Our function is f of x equals square root of x plus 40 minus square root x minus 4. So we're looking for the x-intercepts, and you find an x-intercept by letting y equal 0. Our equation is written in function notation, so we're going to set f of x equal to 0 because that is y. So our equation is 0 equals x plus 40, square root of x plus 40 minus square root of x minus 4. So looking at this, we have a radical equation because we have a variable that is underneath a radical. The strategy for solving this type of equation is to isolate the radical and then square both sides to get rid of it. Now we have two radicals in our equation, so we're going to have to go through that process twice to get rid of both radicals. So I'm going to start by adding square root x to both sides. That gives square root x equals square root of x plus 40 minus 4. So I have one radical isolated on the left. This radical is a square root, so the way we get rid of a square root is to square both sides. I'll square the left, and to balance, I need to square the right as well. On the left-hand side, the square root and the square cancel each other out. And on the right-hand side, we're going to multiply this out. It becomes square root of x plus 40 minus 4 times square root of x plus 40 minus 4. When I multiply square root of x plus 40 times square root of x plus 40, that becomes x plus 40. Let me work that out on the side just so it makes a little bit more sense. I'm doing square root of x plus 40 times square root of x plus 40. And when we multiply radicals together, we multiply what's underneath them. So this becomes x plus 40 squared underneath the radical, and the square root and the square cancel each other out, and you get x plus 40. So it's a little bit messy with the variables, but you can see it very clearly happening with numbers. Square root of 2 times square root of 2 is square root of 4, and that's 2. So it always goes back to when you multiply these radicals that are the same together, it works out to be what's underneath the radical. So if I continue on, I'll multiply the outside two, and one of them has a radical and one doesn't, so I can't mix those, so I'll write it as minus 4 square root of x plus 40, and then I want to multiply the inside two, and that's a minus 4 square root of x plus 40, and I want to multiply the last two together, and that's a minus 16, a plus 16. And I still have x on the other side. I'm going to do a little bit of simplifying on the right-hand side. I can combine these radicals together, and I can also combine these constants together. So that would give me the equation x equals x plus 56, 40 plus 16 is 56, minus 8 square root of x plus 40. All right, so now we're in this part of the process where we have to repeat what we just did over again. We were able to isolate and get rid of one of the radicals, and now we still have another radical in our equation. So we now need to isolate this radical and square both sides to get rid of it. So I'm going to start isolating by subtracting x on both sides, and that gives me 0 on the left. I'll subtract 56. Negative 56 equals negative 8 square root of x plus 40. Divide by negative 8, and that gives 7 equals square root of x plus 40. Now that I've got that radical isolated, I'll square both sides. And that gives 49. The square root and the square cancel each other out. And I'm left with x plus 40. And I'll solve for x by subtracting 40 on both sides. And that gives me a solution of x equals 9. Now there's one more step that I need to take, and we have to do this step anytime we square both sides to try to find a solution. Most of the time, the step where you check your work or check your answer is an optional step that we're doing just to be careful. But whenever we square both sides, it's possible to get what we call extraneous solutions. So checking is actually part of the process when you solve radical equations where you square both sides. So I need to check to make sure that x equals 9 works in the original equation. So in the original equation where I'm starting to find the x-intercept, I'm going to substitute in an x equals 9. So that'll give 0 equals the square root of 9 plus 40 minus the square root of 9 minus 4. That's the square root of 49. The square root of 9 is 3. The square root of 49 is 7. And negative 3 minus 4 is negative 7. And 7 minus 7 is 0. So 9 is a solution to this equation, and that's also the x-intercept of this function. And this question says, use the graph to determine the domain and range of the function. So when I'm finding domain and range from a graph, I like to use a pencil or a ruler to help guide me. So what I do is, first I'm finding domain, and we're going to write our domain in interval notation. And I'm going to hold my ruler or pencil vertically because my ruler, when it's held vertically, is sort of marking along the x-axis, and the domain are the x values. So I hold it vertically, and I'm going to move the ruler from left to right. Now the reason why I go from left to right is because when you use interval notation, you always want to go smallest to largest. And on the x-axis, the smaller side is on the left side. So we start on the left, and I'm going to decide when is the first time that my ruler hits the graph. The first time it hits the graph is at negative 3 at this spot right here. And so my domain is going to start at negative 3. Now looking at the graph, that point is a filled in dot, which means that negative 3 will be included as part of the domain. So I'm going to put a bracket on the negative 3 to indicate that negative 3 is part of the interval, it's part of the set. So going from left to right, the first time I hit is negative 3. I continue to hit as I go from left to right, and I'm keeping hitting the graph all the way until I get to this point over here, and this value is 7, 0. So my domain is going to stop at 7 because I no longer hit the graph after that point. And just like on the last one, that endpoint, 7, 0, is a filled-in circle, which means it's part of the graph, and I would put a bracket on that 7 to indicate that 7 is part of the domain. So I've written down the domain now. That's -3 to 7, including the endpoints. So that notation means starting with -3, including -3, and continuing all the way until 7 and including 7. Then we're going to take our ruler and switch it to horizontal to find the range. And now as I go from bottom to top, I'm running along the Y scale now. And from bottom to top, the first time I hit the graph will be at this value here, which is -2, 0, and range are the Y values. So my range will start at -2. That's a filled in dot, so I'll include -2 in the range. And so going from bottom to top, the first time I hit is -2, and the last time I hit the graph will be at this point right here, which is -3, 6, and that Y value is 6. So the range goes till 6. That's a filled in dot, so I'll put a bracket on that. So I found that the domain is -3 to 7, including the endpoints, and the range goes from -2 to 6, including the endpoints. Okay, so I just got pointed out that there's a mistake in my work here, and just want to go back and explain what I did wrong. So when I went from bottom to top, I said the range starts right here because that's where the first time I hit the graph is, and the range are the Y values. So I wrote down the X value of -2 when I should have written down the Y value of 0. So let's correct that. And we have our range starting at 0 and continuing on until we get to this Y value here of 6. So the range is actually from 0 to 6. So for this question, we want to use the graph to determine the domain and range of the function. So we're using the graph to determine that domain and range of the function. And this may be an unusual looking graph to you. It has some features that you may not be familiar with. We've got these dashed lines that are showing up on the picture. And these dashed lines are something that we're going to be learning about in a later chapter. And they are called asymptotes. So let me just explain what's happening on this piece of the graph here. So if we look at this piece of the graph, I'm having a little bit of trouble with my whiteboard. If we look at this piece of the graph here, when we have an arrow on the end of our line, it typically means that the graph continues off of what we're viewing, off of the screen. So typically, if that dashed line wasn't there, we would assume that the arrow just keeps going down and to the left, or sorry, not the arrow, the graph keeps going down and to the left and down to the left and down to the left forever and ever and ever. Well, it does do that. It keeps going down and to the left. However, this dashed line that we see means that it stops at that line. It's never going to pass that line. So it does keep getting closer and closer to that dashed line. So it does keep going down to the left, but it never crosses that dashed line that we see there. The same thing is happening on this side over here. So because we have that dashed line, which is called a horizontal asymptote, the line is continuing the pattern to get closer and closer to y equals 3, but it never gets there. It just keeps getting a tiny bit closer and a tiny bit closer. And then over here, we have those vertical dashed lines. Those are vertical asymptotes. And the same thing happens. These lines are getting closer and closer to the dashed line, but never reaching it. And the same thing is happening up here as well. So that's a feature that you may not be familiar with. We are going to study it a little bit more later. But with that in mind, let's find the domain and range of this graph. So when I'm looking for domain and range of a graph, I like to use my ruler. And when I'm finding domain, I hold the ruler vertically. And the reason why I hold it vertically is because it allows me to mark off different places along the x-axis, which is important for domain because the definition of domain is all of the x's. So I'm holding this ruler. You might want to use a pencil vertically. And I'm going to go from left to right. And I'm going from left to right because I'm going to use interval notation. And interval notation always goes smallest to largest, left to right. Okay, so when I am looking for the domain, I'm looking for the first time that my ruler hits the graph. So I can use that as my lower bound, my lowest value in the domain, my lowest x value. And then I'm going to look for when this ruler stops hitting the graph as my highest part of the domain. So let's start doing that here. So because of this arrow that we see here, as I said a moment ago, that means that the pattern continues. This graph continues off screen to continue to move down and left, getting closer and closer to that dashed line. And so that indicates to me that the domain is going to start at negative infinity. So as I keep moving to the right, I'm hitting the graph. I continue to hit the graph, and then we reach this dashed line here. So hopefully you remember what I mentioned is that my graph will continue to get closer and closer to that vertical line without ever reaching it. So because it never reaches it, I have a gap in my domain. So my graph does not have an ordered pair with an x value of -2. So that vertical line, that vertical dashed line, is right on -2. And there is no ordered pair on this graph that has an x value of -2. So I'm going to stop my domain at -2, and I'm going to put a parenthesis on -2 because -2 is not part of the graph and it's not part of the domain. However, right after the vertical line, you can see that the graph continues after that vertical dashed line. So my domain starts again. So my domain is going to start back up at -2 and continue until I get to that next vertical line, which is right here at 2. So the same thing happens. This piece of the graph gets closer and closer without ever reaching it. So my domain continues till 2. If I go all along this vertical line, there is no part of the graph. There are no ordered pairs that have an x of 2. So my domain takes a break at 2, but then right after 2, this piece of the graph continues. So from 2 to infinity, I have x values that are part of the graph. So this is my domain. The domain of this graph is from negative infinity to negative 2, union with negative 2 to 2, union with 2 to infinity. So if we think about this on a number line, we're saying that negative 2 and positive 2 are not part of the domain, and every other number on the x-axis is a part of the domain. We found the domain. Now let's find the range. So when we find the range is the set of all y values. We're going to switch our ruler to be held horizontally. Let me erase all my markings here. And I'm holding this ruler horizontally because that's going to mark out different places along my y-axis. And remember, the range are the y's, all of the y's. So I'm going to start at the bottom, that's the lowest y value, and move to the top. So as I look at this, the lowest y value, because of these arrows, meaning the pattern continues, that means that my range will start at negative infinity. As I move my ruler up, I'm still touching the graph, and I continue to touch the graph until I get to this spot right here. And this spot has a y value, that ordered pair is 0, 0, has a y value of 0. So my range is going to stop at 0. That point, 0, 0, is part of the graph. It is included in the graph. And 0 will be included in my range. So I'm going to use a bracket on 0 to say that that point is included. We notice that the graph does not touch, the ruler does not touch the graph for this whole section here in the middle. And it's not until we get to this dashed line here that we have some more pieces of the graph. So my range is not going to start again until y equals 3. Now I'm not going to include 3 because this piece of the graph and this piece of the graph are indicating that the line gets closer and closer to a y value of 3 but never reaches it. So 3 is not a point in the range. So we're going to put a parenthesis on the 3. And then as we continue, you can see these arrows at the top. And these pieces of the graph go on forever, and all of the y values are covered. So my range will continue to infinity. So we found the range to be negative infinity to 0, 0 included, union with 3 to infinity. This question says, determine the intervals on which the function is increasing, decreasing, and constant. So these words, increasing, decreasing, and constant, these are words that are describing y. So let's get a feeling for the overall sections of the graph by tracing the graph as we go from left to right. So starting at the leftmost part, so the reason why we're going from left to right is because on the number line that's smallest to largest. We want to write our intervals smallest to largest. So as we go from left to right, we can see that the y values are decreasing along this section, increasing along this section, decreasing along this section, and the y values are constant along this section. So I'd like to take a moment and label these different sections. So this section is decreasing, as well as this section here. We'll label that with a D for decreasing. And this section is increasing. I'll label that with I. And this section is constant. Now, when we're asked to determine the intervals on which the function is increasing, decreasing, and constant, we're wanting to write down the intervals of x. We use the x-axis as our kind of map, our way to describe directions on where to look. And so when we write down the intervals, we're going to write down the x intervals for which the graph is either decreasing, increasing, or constant. So I'd like to write down this interval, this first interval that's decreasing, and we want to write down the x where that starts and the x where that ends. So we're going to say that it's decreasing on the interval from, let's see, that looks like -10. And that decreasing interval stops at 0. Now, I'm either going to put parentheses or brackets on these intervals. And depending on the definition that's given to you, in some books you use parentheses based on the definition, in other books you use brackets based on the definition. In our college algebra book, we use parentheses, but in the pre-calculus book I use, they would put brackets on those intervals. So we have another decreasing interval here, and that decreasing interval starts at this x value and ends at this x value. So the next decreasing interval is from 4 to 9. And then we have an increasing interval. And the increasing interval is right here, and we can see that that starts at an x of 0 and ends at an x of 4. Once again, our book uses parentheses on this, but pay attention to your book of whether to use parentheses or brackets. So then we have an interval of constant, and that interval of constant will start at this x value of 9. And because of the arrow, it continues on forever in this direction to infinity. So we found the intervals of decreasing to be from -10 to 0 and 4 to 9. The intervals of increasing are from 0 to 4, and this function is constant from 9 to infinity. On this question, we want to use the graph of y equals f of x to answer the question, on what intervals is f increasing, decreasing, or constant? So when we look at this picture, we see this graph in red, which is labeled up here as y equals f of x. And when I'm looking for the intervals of increasing, decreasing, and constant, what I'm going to do is try to look at the picture overall to start with. And what I do is I trace the graph going from left to right. And the reason why I do that is because in the definitions of increasing, decreasing, and constant, all of those definitions describe x sub 1 being less than x sub 2. So that's telling us to go from the smaller to the larger value. And so on the x-axis, the smaller values lie on the left. So I'm going to start on the left. And as I trace over this graph, what I'm going to pay attention to is the y values. These words of increasing, decreasing, and constant, these are words that are describing the y. So as I go trace through this graph, I can see that along this path, the y's are constant, they're not changing. So all of these y values are 4. Then the y values are decreasing along this section, increasing along this section, decreasing along this section, then increasing, then decreasing, then increasing, and then constant. So I want to label all of these intervals, and I'll do that with some different colors. So we said that this section and this section of the graph are constant. Then this section is decreasing. This section is decreasing. And this section is decreasing. And then we have some sections that are increasing. And so we can visually see on the graph where these different sections are increasing, decreasing, and constant. And when we write down, when we try to answer the question on what intervals, this question is asking us to state the x's, the intervals of x, where the increasing, decreasing, and constant are occurring. So when I look at those x intervals, I'm imagining this line being sort of projected down onto the x-axis, and where is that interval starting and stopping. So because of this arrow, it's starting at negative infinity and stopping at an x of negative 6. So we have an interval of constant which goes from negative infinity to negative 6. Now I've used open intervals because the definition in this book gives open intervals, but there are other definitions, other sources where the definition could include closed intervals as well. And a closed interval would be if you had a bracket on this negative 6 instead of a parenthesis. But this book uses open intervals. So we also have a constant interval that is over here that starts at 6, and because of this arrow goes on forever to infinity. So we have the intervals of constant being from negative infinity to negative 6, union with 6 to infinity. So then let's write down the intervals of increasing, and those are the blue intervals that you see. And remember, we're going to be writing down the intervals of x. So this interval of x starts at negative 5 and goes to negative 4. And then we have an interval of x which starts at 0 and goes to 4. And remember, this book uses open intervals, which is why I'm using parentheses on this. And then we have some intervals of decreasing. Those are in this kind of pink color. This interval will start at negative 6 and stop at negative 5. We have another one which starts at negative 4 and stops at 0. And we have another one which starts at 4 and continues on to 5. And I apologize, I've just noticed that I left off an increasing interval. So you can see this little section right here I left off. So there's one more increasing interval which starts at 5 and stops at 6. So if you're going to be answering this question in my math lab, pay attention to the blue writing next to the blank because I believe it says to separate the intervals by commas. So you may be using, instead of the union symbol here, a comma between these intervals. So as our final answer, we have intervals of constant being from negative infinity to negative 6, union with 6 to infinity. Intervals of increasing being from negative 5 to negative 4, 0 to 4, and 5 to 6. And intervals of decreasing from negative 6 to negative 5, negative 4 to 0, and 4 to 5. Thank you for checking out my videos. Have a great day.